A mathematical construction attributed to the Italian physicist and mathematician Torricelli, who was a student of Galileo and the inventor of the barometer, is this trumpet-shaped figure. It is the result of rotating the graph of y equal to 1 over x from 1 to infinity. Basically, the boundary is generated by rotating the graph of y equal to 1 over x from 1 to infinity. Well, here's 1 over x. If we rotate the graph around the x-axis from 1 to infinity, you get a trumpet-shaped figure like this that we see here. This figure is called Gabriel horns very often, maybe because it has infinite size, and so it's not a human thing. This object has infinite length and infinite surface area, which is not surprising, but it has finite volume. These facts are proven using basic improper integration that you encounter in calculus. There are many articles and videos on the internet that work the details out. The links to some of these are in the video description below. We discuss an equivalent problem in this video, but without using integration. Before discussing our paradox, I'll point out how it and the Torricelli trumpet are related to an analogous two-dimensional problem where we have area instead of volume and perimeter instead of surface area. Specifically, we are looking at a flat triangle-like region here with area that is less than a half of a square unit, but a perimeter that can have any length we want, no matter how large. The triangle-like region shares two sides with a right triangle that we see here, and the hypotenuse, however, is replaced with this jagged orange curve whose length can be arbitrarily large. I've discussed this type of curve in another video about a paradox involving lengths of curves. So check that out if you're curious. Because the triangle-like region is inside the right triangle of sides 1, its area is less than the area of the triangle, which is simply 1 times 1 divided by 2, or 1/2. The perimeter, of course, is 1 plus 1 plus the length of this curve, which is L, and that can be arbitrarily large. So we have a finite area and unbounded perimeter in this case. Let's talk about our paradox now. What we have here is infinitely many boxes stacked on top of each other. They all have different sizes, as you see here. The bottom box, the largest one, has a width of 1 unit, a depth of 1 unit, and a height of 1 unit. The green box on top of that has dimensions 1, 1/2, and 1/2. The box on top of that has dimensions 1, 1/3, and 1/3. And the green box on top of that is 1, 1/4, 1/4. Then on top of that, 1, 1/5, 1/5, and so on. We also assume that the stack of boxes as a composite shape is hollow inside, in a sense that where adjacent boxes touch, we cut out the common surface, common rectangular surface between them, so as to create a hollow shape. With all that in mind, let's find out what the total height of the stack of boxes is, how tall it is, what is the total surface area of the shape, and what is its total volume. Starting with the height of the stack, notice that it is simply the sum of the lengths 1 plus 1/2, then plus 1/3, and then plus 1/4, and then 1/5, etc. And basically that gives us a so-called harmonic series, which is very familiar: 1 plus 1/2 plus 1/3 plus 1/4, and so on, infinitely many terms. This series is known to diverge to infinity, or has an infinite sum. So the height of the stack we now know is infinite. Next, let's take a look at surface area. As we might imagine, when we have an infinite number of boxes, the total surface area we expect to be infinite. And that is in fact the case, but to prove it, I'll do the following. I'll show that the total area of all these red color rectangles is infinite. And since the total surface area is bigger than the total area of the red color rectangles, then that would make the total surface area infinite. With that in mind, let's take a look at the big red rectangle down here. Its area, because it has sides 1 and 1, its area is simply 1 times 1, which is equal to 1. The next rectangle has sides 1 and 1/2, so its area is 1 times 1/2, which is of course 1/2. The one on top of that is 1 times 1/3 in area, which of course is 1/3. Well, now you see what's happening. The total area of the red rectangles is once again the harmonic series. And we know that that has to be infinite in length, in value. So the surface area, the total surface area, which is bigger than the total area of all these rectangles, must also be infinite. Okay, finally, let's see if the volume of the stack is also infinite. Let's look at the bottom box. It has dimensions 1, 1, and 1, so its volume is V equals 1 times 1 times 1, which of course is 1 cubic units. The box on top of that has dimensions 1, 1/2, 1/2, so its volume is 1 times 1/2 times 1/2, which is 1/2 squared. Now that's a little different from the length and surface area. And the box on top of that, if we keep going, volume 1 times 1/3 times 1/3, or 1/3 squared, 1/3 squared, 1/9, and so on, 1/4 squared above that, 1/5 squared, and we get a series for volume. We get an infinite series that looks like this: 1 plus 1/2 squared plus 1/3 squared, and so on, 1/4 squared, etc. This series happens to be convergent because, as you may recall from calculus, this is a p series with p equal to 2, and since that's bigger than 1, the series converges. It's actually known that this series converges to the number or fraction pi squared over 6, and this was first proved by the Swiss mathematician Euler. The idea of figuring out what the actual value of this series was called Basel problem, because Basel was Euler's hometown. Basel problem. And I have links to this in the video description below. Let's talk about the painter's paradox now. Here we fill up all the boxes with paint, and since the stack has finite volume, it should take a finite amount of paint to fill up the entire stack. We can actually be more specific if we use the sum of the series, which is approximately 1.645 cubic units, relatively small amount of paint is enough to coat the interior surface of all the boxes if it fills up the entire stack. But we know that the interior surface of all the boxes is infinite, has infinite surface area, so we have a finite amount of paint coating an infinite surface area, and that's the painter's paradox. The nice thing about a stack of boxes is the fact that we can easily modify it to get a stack which has infinite surface area but only finite volume and height. All we have to do is to reduce the heights of the heights of boxes really by squares of the reciprocal. It doesn't have to be just the upper boxes. So as you see here, instead of 1/2, I have 1/2 squared, here 1/3 squared, and so on, where a power 2 has been added. If I add up the lengths of the sides of the boxes, I get the Euler series height is 1 plus 1/2 squared plus 1/3 squared, 1/4 squared, and so forth. And we already know that that is finite. So the stack has finite height. And because it's shorter than the stack with infinite height, we expect that its volume is also finite. And that's not hard to show. Let's look at the volumes here and see what we get. The volume of the bottom box is 1 times 1 times 1, which is of course 1 cubic unit. And the box on top of it has volume 1 times 1/2 times 1/2 squared. And this time the volume ends up being 1/2 to the power 3, 1/2 cubed. The box on top of that has volume 1 times 1/3 times 1/3 squared, and 1/3 cubed is the volume of that box. So we end up with a series for volume that looks like, let's make that green, V equal to 1 plus 1/2 cubed plus 1/3 cubed, and so on. And this is also a convergent infinite series because it's a P series with P equal to 3, and therefore 3 being bigger than 1, we get a convergent series. So in this case, everything is finite. Well, not quite. We actually want to show that the surface area remains infinite, and that will be the punchline. In order to figure out the surface area, in this case, for the stack of finite height, all I need to do is to show that the areas of the red colored rectangles add up to an infinite magnitude, and then that means the area of the entire stack must be also infinite. Down here I have dimensions 1 and 1/2. So the area of the first red rectangle is 1/2 times 1. The next red rectangle has dimensions 1 and 1/2 of 1/2 over here. So the area is 1/2 of 1/2 times 1. The one above it has area 1/2 of 1/3 times 1. The width is still 1, and so on. There's a factor of 1/2 attached to all of these, so that we get a total area of the red rectangles coming out 1/2 times 1 plus 1/2 times 1/3, sorry, 1/2 times 1/2 first, and I'll drop the ones, then 1/2 times 1/3, that would be this one here, and then the one above it will be 1/2 times 1/4, because we're just going with 1/2 of 1/4 up there, and so on. You'll notice that if I pull out a 1/2, I get 1/2 times the harmonic series, which we know to diverge. Now, thinking of this as half of infinity, we should come up with infinity as the answer. And so we see that the surface area in this case is infinite. The stack of infinitely many boxes that we just talked about can be quite small. If we pick the unit of length to be centimeters or inches, then the stack is small enough to fit in the palm of a hand, even though it has infinite surface area. In a way, this is a three-dimensional analog of the triangle-like region that we talked about earlier, which had finite area but unbounded perimeter. Well, that concludes our discussion of this paradox. Thanks for watching.